Hello, and welcome to our discussion of the Cauchy integral formula. We'll begin with a lemma that I'll call the relaxed Cauchy integral theorem. So let D be a star domain with star center Z star, and let F be holomorphic on D except possibly at the point Z star and continuous on all of D. Then, the integral over gamma of F is equal to 0 for any closed curve gamma in D. So this looks almost exactly like the Cauchy integral theorem. We have a function defined on a star domain that's holomorphic. The integral of that function around a closed curve is equal to 0. The one difference is that the function can fail to be holomorphic at the point Z star, which is the star center. The function f still has to be defined and continuous on all of D, including the star center, but it can fail to be holomorphic at Z star, and still the results of the Cauchy integral theorem will hold. The proof of this lemma, unsurprisingly, uses the original Cauchy integral theorem and a bit of an approximation argument. It gets rather technical. I don't think the proof is that enlightening, so we will simply accept it as true and move on. Assuming this to be true, we can state now the Cauchy integral formula. So let f be holomorphic on the open set D, and here D doesn't have to be a star domain or even a domain, it just has to be open. And we'll take a point Z0 in D and a number r greater than 0, such that the closed ball centered at Z0 of radius r is contained in D. Now we know D is open, so that means given any point Z0 in D, we can always find an ordinary ball centered at Z0 that's contained in D. Here I also want r to be small enough so that the closed ball centered at Z0 is contained in D. And then we have the following marvelous formula. F of Z is equal to 1 over 2 pi I times the integral over the circle modulus of Cauchy minus Z0 equals R of f of Cauchy divided by Cauchy minus Z, where here Z is a point in the open ball centered at Z0 of radius R. So what does this tell us? If you want to know the values of f inside the ball centered at Z0 of radius R, if you want to know those f of Z, it suffices to take an integral along the boundary of the ball. So this integral is over the curve modulus of Cauchy minus Z0 equals R. This is the circle centered at Z0 of radius R. So the behavior of f on the boundary of the ball, sort of a one-dimensional subset of the complex plane, determines the behavior of f inside the entire ball, which is a two-dimensional subset of the complex plane. And this formula for f, like the Cauchy integral theorem, will be extremely useful for calculating various quantities and understanding deeper properties of complex functions. Let's prove it. Here is something I can do. There is a number capital R greater than 0, such that the closed ball centered at Z0 of radius little r is contained within the open ball centered at Z0 of radius big R, and this second larger ball is still contained within D. And I can do that because of some more technical topological properties of the complex plane. Trust me that this is true. Now this ball centered at Z0 of radius R is a star domain, because all balls are star domains. And it's contained in D, and we know how f behaves on D. So let's fix a number z and define a new function g of Cauchy by the following two options. G of Cauchy will be f of Cauchy minus f of z divided by Cauchy minus z when Cauchy is not equal to z, and it will be f prime of z when Cauchy is equal to z. Now we know that f is holomorphic on D. We know what that first option for G looks like. That's just the difference quotient for f based at the point Z. So it should be pretty clear to us, I hope, that G is going to be continuous on D. Certainly when Cauchy is not equal to Z, G is continuous. You have no division by zero problems. And at Cauchy equals Z, Well, G is continuous just because the limit of the difference quotient is f prime of z. And moreover, G is going to be holomorphic on all points in D except at z. Why? Because at all points in D except at z, G is given by the difference quotient, and that's a quotient of differentiable functions as long as C is not equal to z. Now, something else. This point z that I'm using in my definition for G, that is a star center for the ball centered at z0 of radius r. Why is that? Let's assume the point z is in this ball centered at z0 of radius big R. Then a fact about star domains is that balls are always star domains, and the star center of a ball can be any point you want in that ball. So what do I see? G is continuous in particular on the entire ball centered at z0 of radius r, and it's holomorphic on that ball except at the star center z. So we can invoke the relaxed Cauchy theorem. And this is going to tell us that the integral over the curve modulus of c minus z0 equals r of G is equal to 0, because G has met all the hypotheses of that relaxed Cauchy integral theorem. Let's do some calculations. So 0 is equal to the integral over the curve modulus of c minus z0 equals r of G. And what is G here? Well, I'm taking C such that C lies on this circle modulus of c minus z0 equals r. And G is one of two things, depending on whether C equals my point Z or not. And my point Z satisfies modulus of z minus z0 is strictly less than r. So Z does not lie on this curve. So for all C on this curve, I can replace G by the difference quotient. So 0 is equal to the integral over modulus of c minus z0 equals r of f of c minus f of z over c minus c. And now let's just do a little algebraic rearrangement here. I'll separate the integral into a difference of two integrals. The first integral will be integral over the circle of f of c divided by c minus z. The second integral, I'll do the subtraction. My integrals here all depend on c, so f of z is constant. So I'll pull that f of z out, and I have now minus f of z times the integral over the circle, dc over c minus c. Now this first integral, f of c over c minus c, we can't do anything really with that, but we don't want to. We want an integral that looks like that in our final answer. But what about this integral over the circle of dc over c minus c? We know what that integral is. We've calculated it before. That integral is 2 pi I. So what do we have here? 0 is equal to the integral over the circle modulus c minus z0 equals r of f of c divided by c minus z minus f of z times 2 pi I. Rearrange, divide by 2 pi I. You have yourself there the Cauchy integral formula. And as an example, let's evaluate the integral over the circle modulus of z equals 1 of cosine of z divided by z. So this is the integral over the unit circle. And one thing to try to do whenever you get complex integrals in your life, can you use the definition? Can you use independence of path? Can you use one of the Cauchy theorems? And hopefully the answer will be one of the above. So if we put f of z equal to cosine of z, that's the numerator here, then our integral becomes the integral over the unit circle of f of z divided by z minus 0. Now this second integral looks a lot like the integral that we get from the Cauchy integral formula. And what do we know about f? F is cosine of z, f is entire. So this second integral we can evaluate with the Cauchy integral formula. It's 2 pi I times f of 0. What's f of 0? F is cosine, so f of 0 is 1. And so this integral becomes 2 pi I. And I claim that trying to do this integral by definition would be singularly nasty, and independence of path simply doesn't apply here, so we use the Cauchy integral formula.